Okay, so today we are going to start this series in which we are going to talk about reinforcement learning. काफी सारी चीजें हम लोगों ने अभी तक देखी हुई हैं. Out of that, there is a new paradigm, and it's a completely different sort of paradigm in which we try to learn things from. You can see that from the raw data we wanted to learn, and anyways we used to work on the raw data, but the point is that it's going to be agent and environment. So environment and agents. So agent need to be completely in an unsupervised way move into an environment, and started to understand that what's the dynamics of the game that this environment is actually following, and started to behave in such a way so that somehow managed to live inside this environment. So environment अलग अलग तरह के हो सकते हैं, and that we will talk about. And depending upon this environment, we need to fix up our goal कि हमें actual में output में किस तरीके का goal, what is the goal this agent need to somehow understand the dynamics and achieve that goal. So anyways, this lecture is being completely adapted from this CS231, and so here you can see that. So in artificial, so this whole thing is actually artificial intelligence. Out of that, few algorithms are actually machine learning. There are other algorithms as well, and within that machine learning we can say supervised and unsupervised, and out of that there is something, so they supervised, is unsupervised, there is reinforcement. And in all of them, for supervised or unsupervised or reinforcement, we can say that we are having um, deep learnings, and this is the area in which we are going to be interested. So reinforcement learning देखनी है हमें, और पूरा reinforcement learning नहीं देखनी है. We need to see about few things कि reinforcement में वो किस तरह से किया जाता है, और उसके बाद हमें देखना है कि उसे हम अपने डीप न्यूरल नेटवर्क से किस तरह से recently solve करने लगे. So three major paradigms we all can understand, that supervised and unsupervised. So just an overview कि हमारे पास data होता है जिसमें we are having our x as the data, y as our label, and what we need to learn is that we assume that when we see this x data, we are going to get this y label. So so we need to learn a function that as soon as I see this x, I know a way by which I can convert it into y. अगर ये एक फेस है तो मैं कह देता हूँ कि ये आदमी का फेस है कि औरत का फेस है, मे बी दैट्स अ सुपरवाइज्ड. सो फॉर ईच एंड एवरी गिवन training data, we actually know that what is the data and what is the label, and using this information we started to work over this and try to learn a function which can automatically later, once when see this x, some apply certain things and find out this y, what is this label. So essentially a different example of such thing is classification between cat and dog, object detection, semantic segmentation, regression, image captioning, whatever, in which you have x and the corresponding label y. In the case of unsupervised learning, we all understand that only data is given. We do not know that what are the labels associated to that. And once label is not known, then what is the goal? What is the goal or the whole sole objective of such learning? So suppose that if I give you huge amount of images of, I have not said that what are the actual classes. I just say that huge amount of data is there. And then our goal is that we assume that this data is actually following some underlying hidden, hidden relationship between this data is there. And suppose that there are few images which are cat images, there are few images which are dog images. We do not know that they are cat or dog, but they are having some sort of relationship. Or there are some face images and there are some car images. So they are having, multiple cars are very loosely associated to each other, but they, with respect to association between a cat and a car, there is a big amount of association which is happening between cat images and the dog images. So can we learn such type of relationships? So basically the type of problems that we used to handle in that type of scenario is that clustering, dimensionality reduction, or the feature learning, or density estimation as well. So what happened that in the case of, or in the absence of target underlying target, so there is no target, then underlying data we assume that it's going to be coming from some probability distribution. And if I can somehow learn that distribution, that from which distribution such data is actually coming, training data is coming, then whole amount of things can actually be we can do. And you can see that that sort of things are actually being done in the case of GANs, generative adversarial networks, in which they try to learn this underlying distribution. Now it comes that a completely different scenario in which reinforcement learning is going to happen. First important thing that one should have to understand is that such paradigm is going to talk about the exploration. So we do not have any information about the about the environment, that how this environment, what this environment is going to behave like. This environment is behaving in a very different way, and how you can know that how this environment behave is that, being an agent, you need to go inside it and 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 take your decisions, and depending upon your decision, that's actually being called as exploration. So it's completely new world in which you go, do things, see that what type of rewards or penalties that you are going to get, and then you keep on understanding that okay, this is the environment and this is the way it's actually going to behave. So being an agent, we need to design an agent, we need not to design an environment is anyways being given to us, but assuming that we need to come up with an intelligent agent which will, like AI bot, go inside an environment and explore. By exploration it will learn, and it's actually the same way humans also take any environment, go inside and learn accordingly. And and then once you understand that how this environment is working, and then you can use your learning to explore in certain things which are non-trivial as well, and you started to behave well in that game. So it's completely relying upon the hit and trial way, and that is why it takes good amount of time to be learn something meaningful. And its strategies are one should have to understand that how one can behave optimally within that environment. So optimally is actually a word that one should have to be looking for, that how you can learn a behavior which is optimal. And these are the few key ingredients, or you can say that the few basic things which are required for the setup of an RL learning. So first thing is that we just go with this numbering 1 2 3 4. So there is some environment, and there is an agent, and this agent, so what happened is that as soon as this agent got initiated, environment is going to give you a state. So your agent is going to be in a particular state, say ST, and at this state, when agent is there, this agent is at state ST and take an action AT. So environment has given this agent this state, it has taken an action, and because of this action, environment understand that okay, this action has been taken, and depending upon this action, we are going to get a reward. So that is going to be the reward. Along with this reward, environment is going to give this agent a new state. So environment is the way in which environment is behaving is that it's actually giving these states, environment is giving the rewards, and these state and rewards are actually being dependent upon the previous state of the agent as well as the action that it actually have taken. Yeah. So so all these things are actually being written over here, that the agent A is at some state ST and at some time T. That's why it's being written as T. So S is the state, T is the time. It is interacting with the environment E via few defined set of actions. So these actions are being fixed, or in any game or in any environment you cannot take each and every action. And even if it's actually a learnable, or you can say a digital environment, then actions must have to be somehow discretized. So we are assuming that there are A1, A2 and so on up to some finite number of actions. And action at any state is chosen only by utilizing the state. You are only utilizing the current state of the agent, and that is why it is assuming that since next action or the state, everything is going to be dependent only upon the current state of the agent. This is actually the Markov assumption, And that is why this whole RL field is actually or the RL learning paradigm can be formulated using Markov decision process. So Markov random process is something, we'll talk about that. And then Markov decision processes are the the tool by which this whole RL learning paradigm can be formulated. So which essentially means that no history is required. Only the current state of the agent is sufficient to tell that what is going to be the next action as well as what is going to be the next state. Now at any state ST, taking a particular action AT is going to fetch you a reward. So there is some reward function depending upon your environment, and you are going to get that function, that reward. Now, now there has to be a goal of such an environment, that if there is an environment, sorry, goal of an agent. So given a particular environment, agent move inside and started to play it as a game, but it need to fix up some goal, that I need to do this thing, I need to maximize this, I need to minimize this, I need to do certain things. So that is the goal. And by in general, the actual goal is to basically learn optimal behavior. As we have said, optimal behavior need to be somehow quantized, and that's being done in terms of to learn how to take an appropriate optimal action so as to maximize the reward. So being an agent, you need to somehow manage that what should I do at any state, what should I do so that I get the maximum reward. And as I say that the maximum reward, it should not be a greedy approach in which you are at a state and you are just looking that I can go here, here and here, and then see that okay, if I go here then I'm going to get R1 or R2 or R3, and then you say that this is the maximum, I'm going to choose this. No, that's actually the greedy approach. Here it is going to be the future discounted reward maximization. We will talk about this, that why do you require discounted and what is the meaning of this future reward maximization. But the point is that one should have to understand that we need to learn a optimal behavior, which mean to say that agent is at a state, say ST, it need to move to a state by taking such an action. It has to move in a state, next state, like this. It has taken 80, move into a state which is going to give you the best possible returns throughout your life. When you stop, you are going to, so you take this action in such a way so that if I choose this state, why I have chosen this state or have chosen this action so as to move into this state, because from here if I keep on moving, I'm going to get the best possible reward. So that is the optimal behavior. It should not be like that from here I just choose that what is the maximum or the minimum, in that direction I should be moving. It is that if I keep on doing the same thing, I am going to get the best possible reward, and that is the optimal global the maxima of your reward you should be you can achieve. So we will talk more about this. As I've said, that Markovian decision processes can be used to formulate such a things. That's why MDP we are going to learn. And two major class of RL algorithms are actually, first one is the Q learning and next one is the policy gradient. And then there is another algorithm, that's actor and critic algorithm, which is using or the combination of both of this. So these are the things that we need to somehow cover in our upcoming classes. Basic RL setup, we all understand the things which are happening, and exactly the same thing is being written again just to formalize the whole thing. Now we have to understand that this RL is, there is no training data at all. You all understand that I am having an environment which is behaving in a certain way. We'll talk about that, what is the meaning of an environment. Right now you assume that it's some game, and you need to design an agent. An agent is playing this game, and you move your cursor here, you will get -1. You move your cursor here, you will get +1, and you take all different possible actions, keep on changing your state, and at last environment say you lost, or at last environment say that you win. And then you understand that what one should be doing so as to learn a winning strategy. So when there is no training data at all available, then what one should have to do? So here it comes that the episodic training, and which essentially mean that these are, the 6 steps which are being there. One, environment. Two, agent. Agent is giving a state. With respect to this agent, this state, agent has taken an action. Given this action, agent environment understand and give you a reward. Once you have got a reward, then you have got a new state, and once you have got a new state, you keep on repeating the whole thing. So then you have got a new state. Environment is going to say, so with respect to this new state, you take some new action. Environment will give you some new reward and some new state, and keep on doing. And you are actually generating an episode. So this is one dry run of your game. You keep on playing that game, and once you win or lose, you have got an actually episode. And this episode is saying that once you reach to a terminal state is the final state where you have got your reward, which means that whether you win or lose or whatever. So the episode continues until the environment provides a terminal state to the RL agent. There has to be few or many or one, depending upon the game, terminal states. And once your agent achieves that terminal state, it stops, and that's actually being assumed as a episode. So given such thing, you have got the 6 steps. You keep on repeating these 6 steps, and you will get an episode. And once you have got an episode, you play it multiple times, you will got multiple such episodes, and you can use, and for each and every episode, you also, somehow, at every after every episode, you are, you understand that I've got a reward, or I have got a punishment, basically how much amount of reward that you have got. And depending upon that, what you have done so as to get that reward, those actions should be, the probability to select those action during those states, and they are going to be, they started to get, maximizing. So that is the point that is going to be happening, that you play game, explore the game. There are multiple actions at each and every state. You take an action, and then you fail, and then you understand that okay, we need not to take this action because I'm keep on failing. Then I take some other action and keep on doing till you started to succeed. So it's completely hit and trial. It's completely exploration, learning via exploration. And definitely because of all this, it's going to take huge amount of time for training. So let us see a few examples of such learning. Carpool problem, in which you are having a car. Then this is the vertical, and you have got a mass over here, and there is some some mass is there, and at an angle of theta right now it is, and we need to move our car F in such a way which is having a capital mass M. We need to apply some force F in such a way so that your mass is every time vertically aligned. So the objective is to balance the pole on the top of a movable car. So we are just giving you that what's the way in which RL problem can be formulated, basically, abstract way of formulating an RL problem. So objective is this, and then you will have to tell that what are the states. Then the physical state of any such system can be that what is the angle, what is the angular speed, position, horizontal velocity, maybe few more. What action that you need to take is so you can see that this is the objective, this is the state. What are the actions? Horizontal force that you need to apply. So horizontal force you are going to apply. So when the direction is fixed, then you will say that I am going to only apply force 1, force 2, force 3, and force 4, or 5 or 6 different types of forces, and all of them are in the horizontal direction. And then you will say that what is the reward, and for each time, if the pole is upright, that is the reward. So if at this point my pole is here, and if I move in this direction, then you understand that the reward, we are not going to get reward because it's going to go down. We need to move in this direction so that it move in this direction, and so that it becomes upright. So this is a cardboard problem. Example, you can see the Atari game. You all understand that games are there in which Atari and Contra, Mario, and so on. So if you wanted to build or learn some strategy for that sort of agent, then you can say that my objective is to finish the game with the highest score. State can be, so good thing is that here these are the things they started to use convolutional neural networks, and the state is going to be the raw pixel input of such game screens. So you keep on playing, and you keep on saving those screens, and use those raw image pixels to train your network, so nothing else. And what they have shown is that if you play all possible Atari games, there are many Atari games, 32 or so, and they, using the same algorithm, they have generated agent which can easily play all these games using the same single the network, and same, everything remains to be the same, only you are changing the game, and network is learning the winning strategy for Mario and Contra and so on, which means that the environment is changing, but network learning remains, or the agent learning remains to be the same. So you have got multiple agents, one is playing Contra, other one is playing Mario, and using the formulation that we are going to talk about via MDP, but essentially they are using deep Q learning that we will talk about once we understand all this stuff. So what's going to be the action? Action is going to be the game controlling action, that's say left, right, top, bottom. So there are few actions. There may be few more. I mean, depends upon the game that how many actions are there, but they are not infinitely many. But yes, states can be infinitely many, but your actions cannot be. And then the reward. So at each end of the episode, if you win or lose, depending upon that, you will get a +1 or a -1 sort of reward. Okay, so now with this basic assumptions and basic motivation and introduction, we need to understand formally that what mathematical formulation of such RL system, RL learning can be. So as we understand that Markov property is going to be used. So what does it mean? Is that you are at a state ST. So what is the probability that what's the probability of ST plus 1 to be the next state given the probability given ST, you are going to ST plus 1. The probability is going to be equal to the probability of ST plus 1 given all possible states. You can see that it doesn't matter if you give me 1 or the last state, or you give me the full states, all possible states, because it's whatever is required. This says that whatever is required to estimate or learn that what is going to be my next state, everything is being encoded inside this. One thing is that you may say that the history is not required, or you can say that history is itself is being encoded inside this. So whatever historical things which are required, that may be useful to tell me that what is going to be my next state, everything is going to be encoded inside this ST. So state captures all the relevant information from the history, and state itself is sufficient for the future state estimation. So that was the Markov property. And if you have a process which is following such Markov property, then you say that that's a Markov random processes. Now the point is that we are not talking about Markov random processes. Over that, we are going to have one more thing, that if you have a Markov random process and then you take certain decisions over that. So from Markov property, we are moving towards Markov decision processes, which means that at each state, you are not only going to the next state, but you have a choice of making some action. And once you have a choice of making some action, then then it's actually started to talk about the decision. So at each and every state, you need to choose that what is the action that I can choose. And once you choose an action, depending upon that state, there has to be a proper way by which you decide that what has to be a proper action, and depending upon your action you keep on moving. I just have shown the way in which you're, depending upon your action, environment is going to give you the next state as well as the reward, and you keep on doing that. So that's why you can see that Markov decision processes are going to be used so as to model environment agent and RL learning problem. So in Markov decision processes, these are actually the 5 tuples which are actually required. S is actually, you can say S is the set of all possible states, S1, S2, S3, all the states that are possible. And as I have said that this can be infinitely many for playing games and other things. Previously, suppose that if I show you, so we'll talk about few simple problems in which these states are not infinitely many, and then you can use different types of solution. But once these states started to become infinitely or exponentially many, you require different types of solution. So we will talk about them as well. So given these states, that then at each state there are certain set of possible actions that you can take. Then there is a transition probability matrix, which means to say that that at state st, if you have taken 80 action, then by what probability you are going to be in this state. So this transition probability is going to tell you that if you give me the current state and the action, I can give you that what is the state in which you can go. So that's the transition probability. And then this is going to be the reward function. Exactly same input is going to be there, that at state this, if you take this action, I'm going to give you this much reward. And the final thing is that how much amount of this discount factor that we are going to have. So discount factor, we'll talk about that, but it essentially means that at t equal to 0, I'm only, or I'm interested in say reward that I'm going to get immediately, and after t equal to 1 and 2 and 3 and 4, at say t equal to 50, you are going to get another reward. Then how much amount of weight that you want to give to this guy, this weight. And suppose that if your gamma is equal to 1, then all of these are going to get all the intermediate rewards that you are going to get. They are equally important. And if gamma is between 0 or 1, and very close to 1, or very or is it, if suppose that gamma is equal to 0, which means that I'm only going to give the immediate reward, the most important thing for me, and anything which is coming after this, I'm not giving that reward. So this is the myopic and long-sightedness in terms of reward that we are talking about. But we will talk about in detail that why such a discount function is actually required, instead of just directly saying that giving each and every future reward the same amount of it. So you can see that for any state st and taking an action 80, this is also called as the action and state pair, action and state or state action pair. If you give it to the p function or the probability state transition probability matrix, it's going to tell you that what's the st plus 1, and the same thing is given to the reward function, you are going to get the reward. State transition matrix, as I have said, that's going to be P, and it's a Markov process or Markov chain. So it's a memory less, as I have said, that it's only going to remember the previous thing, and memory less random process. It doesn't remember that what's the history, and iteratively sampling as per the given this probability matrix, starting from some seed. So initial state is going to be given to you, and if you have a probability function like this, then initial state and the action that you have taken at that state is going to determine that what's going to be your next state. So you are here, you take an action, you go there, then you take an action, you go here, then you take an action, then you go here, and keep on doing all that stuff. This is actually a cycle. That's actually can be said as the Markov random process, or the cycle, or the chain that you are having, which is actually a memory less thing. So the full game dynamics. So the good thing about it is that the full game dynamics means that the rules and the regulations of the game can actually be encoded within such a P. At any state, if you take an action, you need to go to this state, and if you carefully figure out that carefully figure out that given a game like this, given a game like Ludo, you are at a state which is actually a number 5, 10, 15, or whatever. And by what probability, or if you take an action like this, where you are going. So it's if I take if you are at 5 and you have got your action like dice number, and that is 5, then mostly you are going to be at 10, and that's almost fixed for the case of your Ludo. But suppose that at 10 there is a ladder, and suppose that at 10 there is a snake, so that is going to change this probability. So the whole Ludo game, or one such a single Ludo game, you play multiple times, and such thing can actually be encoded inside the type of transition matrix that we are seeing, which can say that from 5 there is a very high probability that you are always going to be on 10 if you have got 5. But from 6, if you have got 10, from 6 if you have got 5, then at 11 you are not going to 11, because 11 there is a snake, and you are going to be on say 2 again. So from 6, after getting 5, you are going to 2. So this can easily be encoded inside a transition matrix. So the whole game rule can actually be encoded inside a state transition matrix, and it's being represented in this way very easily, that at state S, if you have taken an action A, then given state X taken an action A, what is the probability that you are going to be at st plus 1? St plus 1 is going to be S dash. Means that from S to S dash, if I am at state S and have taken action A, then what is the probability that I'm going to end up in S dash state? It's a state transition matrix, straightforward. In most of the places you must have seen a similar type of state transition matrix. Immediate reward function is going to be very easy, which mean to say that at state st, if I take an action this, then what is the reward that I'm going to get? This is just the immediate reward, that at this state st, I take an action at, and I have got a reward rt. Just plain same. It's just a table by which you just see a state action pair is being given, and you have got the corresponding reward. So the point is that in the case of such an MDP, Markov decision process, we are not interested at all in the immediate rewards. What we are interested, so let us see what are the things in which we are interested. So suppose that this is my initial state, and at this initial state, and that's why I've written that t equal to 0, then t equal to 1, then 2, then 3, 4, 5, and 6. Okay, and initial state is say st, which was equal to s0, and then s1, s2, s3, s4, s5, and s6. So these are the states that you have got, and how you are going into these states. And if at s0, if you have taken a0, then you have gone to s1 and you have got a reward r1. At s2 you have taken an action this, and have gone to this state and have got this reward. So this is the way the whole thing is happening, and this is one such episode. And here you have got your terminal state, and you've got terminated, and this is one episode which is being end. Now how you are going to get what is the next state? This probability function is going to tell. State transition is, you just give this to state transition, it will tell you that where you need to go. If you give the same thing to your reward function, it's going to tell that what is going to be your reward. Once you have got such a trail, what is the goal of such an agent? This is endlessly moving, or moving in without any goal. So maybe some random things your agent is doing. What your agent need to do is that instead of maximizing the immediate reward, what does it mean? This means that at this stage you need not to worry about anything. You just see that what are the possible places where I can go, and then choose the one where if I go, then I'm going to get the maximum reward. So that is the greedy strategy, and that is the immediate reward maximization. We did not want to do that. What we wanted to do is that at this state, if I choose this direction, why I am choosing this direction? Because out of all possible ways, if I go here, then when I keep on using the similar type of strategy, at some point I am going to terminate. Where I am terminating, what is going to be the future reward? The future reward is going to be R2, R3, R4 and R5. You add all of them. Now the point is that are you looking to add them, giving each and every one equal amount of weight? And that can also be possible. So that is average cumulative reward, average future cumulative reward. When But then you can say that it can be average discounted cumulative reward, which means that I wanted to give more weight to this, and as soon as I keep on moving, I wanted to give them lesser weights possible. So we'll see that how this discounted rewards is actually being done. But essential point is that instead of maximizing the immediate reward at any state, we need to take an action which is optimal, which globally optimal, which means that it should maximize the discounted cumulative future rewards. That's the term that I used to say it as discounted cumulative future reward. So our goal of any MDP is to maximize the DCFR, and then comes one more thing, and that is, instead of average of such a discounted reward, we need to say that it's going to be a expected DCFR, because this is a random process. So instead of you know doing something, because at this state, next time you are not going to follow the same path from this state and the same action, probably you may move into some other thing, and then move into some other thing, and then move into some other thing, and at all of them you are going to terminate at different places. So we need to see that what is this reward, what is this cumulative reward, what is this cumulative reward, what is this cumulative reward, and then we need to figure out that what is the expectation of such a reward, and we need to maximize that. We need to figure out that strategy by which I need to choose my action, so that whatever the direction in which I go, it's assumed that my discounted cumulative future reward is getting maximized, and its expected value, because it's going to be a random process. How MDP operates and can be used to obtain different episodes, we just have seen that you just sample your initial state from some distribution, because all these states are there, and initial state is also going to follow a particular random distribution. Suppose that you are playing Atari game, then every time the first Mario, the first screen is always going to be fixed, so that is going to be your S0. Or there is some probability distribution from which your first or the initial state is going to be chosen. You choose from there for t equal to 0 until it terminates. You let your agent choose the actions. Your agent is going to choose an action, and here it comes that how your agent is going to choose an action. We need to talk about this, and that is actually very, very important part. But there is, suppose that some oracle which is telling that or helping your agent that if you are at state ST, you need to take this action 18. So how you are going to get this action from this state, that we need to figure out, we need to talk about. But suppose that that ST, I have taken is action 80, then environment is going to tell you that what is your next state. So that is being known, that is via your probability distribution, state transition probability. So so the agent can select an action 80. How? That we need to figure out. But it has to have a policy. Policy means that a policy is something that is going to help you to decide your action. At any state, policy has to be there, which is going to tell you that what action need to be taken, and there has to be a rationale behind the policy. Policy need to fulfill a goal. What is the goal here? To maximize your expected discounted cumulative futures rewards. Discounted cumulative future reward need to be maximized. So your policy need to be in such a way so that it maximize this. And if it is maximizing this, then use that policy, and at ST, if you use that policy to figure out that what is going to be your next action, that is globally optimal behavior that you are actually learning, that in whatever state I am, my policy is maximizing this stuff for me, which means that globally I am going to get better and good rewards. But the point is that as soon as at state ST, for the game dynamics, you have ST, and then at ST, your policy has told you to take this action. Once you have taken this action, you have got a reward, and environment has given you the next state as well. So environment has given you RT, the reward, as well as the state, using your R function and T function. How it is being defined, both of these things are anyways being previously seen, that what is this state transition probability, given S and A as your initial or the current state and the action, what is the probability of getting or going into this state. Similarly, what is the expected reward that you are going to get if at this state you take this action. This remember also that at any state S, if you take action, fix action A, then you are going to be in some state S dash. It's not always true that in the you are going to go always into the same state again and again. At a state, sorry, so at state S, I choose an action A and then end up in say state 1, maybe in state 2, and maybe in state 3, with probability 0.7. I'm going here 0.2 and 0.1. That is why your expected, so here you will get your reward as a total cumulative reward is say R1. Here say cumulative reward R2, cumulative reward say R3. Then the expected value is going to be this multiplied by this multiplied by this, and this multiplied by this. So at any state, it's not going to be always true that at this state, if you take an action, then always you are going to end up at the same state. It may happen for certain games, but here the transition probability is going to tell you that if you give, sorry, reward function is going to tell you that what is the reward. And since it's actually a stochastic process in which given these two, every time you are not going to end up with a fixed probability 1 by probability 1 to this state. So that is why with a certain probability you are going this state, with certain other probabilities you may be going or end up landing up in some other states. Depending upon that, what is the expected reward that you are going to get given a discounted. So discount function we will again talk about. So at state S, I go to S dash using this state transition and the reward function, and I have taken an action A. So at S, I take an action A, go to S dash, using these two functions, I will get the expected reward as well as the next state. Now it comes that, so till now what I have said, we have talked about is that the formulation of such an MDP. And MDP, suppose that you want to learn an RL agent which is going to play a game for you, then all of these things are fixed. You need not to talk about this 5 tuple like state, actions, probabilities, reward functions, and gamma. All these things are almost fixed, and that is why MDP is fixed depending upon your game. Depending upon your game or the problem in your hand, all these things are fixed. Now the problem or the actual thing is that you can generate multiple episodes the way we just have talked about. This way we can generate all these episodes, but the point is that how you can take an action. Is there a way by which I can take an action? Because I didn't have talked about that if I give you ST, who is going to give you the next state? And that is essentially the policy. And that is why policy learning, policy gradient, policy improvement, policy iterations are going to happen. And we need to come up with ways by which we can start with a policy and train our networks or other possible training mechanisms so as to come up with the better and better policies. And at some point of time, we need to come up with a policy which is optimally behaving optimally. So how to take action, that is essentially a policy. Here we are denoting it using pi. A policy pi is just a mapping of states to the action. So it will take something from this state space and convert it into some action space. So take some variable at the state space and converting it into a action space. That type of mapping it's actually doing. And what it actually doing is that this pi is actually saying that at st, given st, what is the action that you need to take. And this is not the thing which is which is being known for any game. This is the thing that you need to learn. So being an agent, you need to learn a policy that behaves in the optimal way. So at state, what is the action one should have to take, which means that I need to learn a probability distribution that that if I am at state this, with what probability I need to go to this action. So the goal of an any so first thing is that can actually be the way in which you can choose an action and basically generate an episode as well, because at every state you need to take an action. An agent, that is the code for an agent. Agent need to learn such policy, but it need to learn not chaotic or a random policy. Probably it can also use a random policy to start with, that if you are an agent, you can move in 4 direction, then uniformly, randomly, I am moving in all possible directions. That can be a initialization of such a policy. It can be possible, but the goal of such an MDP has to be to come up with the policy which is optimal policy. The objective of an MDP, or the solution of an MDP, if I give you an MDP or Markov decision process, or a game scenario which is being formulated using such a Markov decision process, as an RL agent, you need to learn a policy pi. And what type of policy you need to learn? You need to learn an optimal policy, that is pi astic. And what has to be the goal? The goal is to learn such a policy that can maximize my DCFRs, discounted cumulative future rewards. So we ensure so we are ensured that the guy who is helping me, this pi astic, which is an oracle for me, so agent has learned this, and that pi astic is going to tell you that if at any state, if you take this action, you are going to get the maximum discounted cumulative future rewards. And if you understand that any optimal behavior, if you take and choose any sub part of that optimal behavior, it also have to be optimal. We all understand that if it's the shortest path, in between anything if you take, that's also have to be a shortest path. Otherwise it's not possible that the whole thing is actually a shortest path. So which essentially means that is the best DCFRs that you are going to get. And that is why MDPs are mostly being solved using dynamic programming. So dynamic programming is actually being used to come up with different types of MDP solutions for different MDPs, and we will see how it's actually being done. Now let us talk about why this discounted rewards and what is the exact meaning of the discounted cumulative future reward. So just see that we are having so we are at t time equal to t. So you will get RT reward, and then you will get RT plus 1 reward, RT plus 2 reward, and gamma is between 0 and 1. And if it is 1, then all of them are going to get the same weightage. If it is 0, then only this is getting the value, others are getting 0. And your GT, or the discounted cumulative future reward, is being defined in this way, which can be written as a GP, geometric series, like this, in which your K is starting from 0 to infinity, your T is starting from T, and that is why K is being added over here. So it's first RT, then gamma times RT plus 1, then gamma square RT plus 2, and so on. If your value is close to 0, it's actually myopic evaluation. If it is 1, then it's far-sighted, or you actually care about your future rewards. You do not care about future rewards. You care about future rewards. And why you required such a discounted thing is that future is uncertain. Because why this future is uncertain, and that's also being explained over here, that we are actually predicting using an inaccurate model of our solution. So our environment is there and we are solving it using a prediction is actually being happening, and things are inaccurate, things are random in between, and the future is completely uncertain. And if that is the case, it is not that at year number 1, if I invest 1000, I wanted to give more and more weightage that what I'm going to get after 5 years or 10 years. No, 5 years what I'm going to get, I give more weightage. 10 years I'll get less weightage, or 50 years I'm giving even lesser weight. So you can see that if everything is uncertain, then initially if you have 1000, some guy will say that I'm going to give you after 5 years, I'm going to give you 1000, it will be converted into 5000. After 10 years it will be converted into 1 lakh. So you will say that okay, in 10 years 1000 may be converted into 1 lakh, and then 50 years it will be converted into 500 crores. So you will say that no, I am not interested in this, or I am interested but I will give very less weight to this because I am interested more in this. So that is why this sort of mechanism or the phenomena is actually required to understand the real behavior for discounting. But the main reason is that our prediction that we are doing, that is actually inaccurate, so future is actually uncertain. Similarly, it is mathematically convenient, that is also one way. And infinite rewards, if there is some cyclic process, and you got into a cycle and keep on getting the rewards and so on. So what will happen is that since it is discounted, then at some point of time it doesn't become an infinite cycle in which you move into to get the reward. Yes, so till now, let us say that if you are having any question, then you can ask. Is there anyone who is having any question?